Some of my best memories playing games are when I was playing with friends, whether it was sitting on the couch together enjoying a round of Mario Kart or Halo, playing a shooter online like Overwatch, or sinking hours into RuneScape or World of Warcraft. I've always had the most fun playing games with my friends. Ever since I've learned to make games, I've always wanted to add multiplayer features. Even back in high school when I was just learning Java and programming board games, I added pass and play features and then added online functionality as soon as I learned how. Being able to test and play my games with my friends has kept me going and made my game dev hobby much more enjoyable. And if you write your own games or play games, I think you'll find learning how multiplayer works interesting as well. You might have been thinking this already, but multiplayer games vary greatly, and making a pass and play game is very different from an online shooter. Let's talk about the different kinds of multiplayer and what makes them unique. To start off, we can divide any kind of multiplayer game into two broad categories: offline games and online games. And the categories I'll be going over is not an exhaustive list, but it is a good way to think of multiplayer games for the purposes of game design. At a very high level, offline games are often played on a single computer, while online games require multiple computers to talk together. Starting with offline games, you might think of something like a couch co-op or split-screen games like Mario Kart or Halo, where a game can split the screen between each player. Additionally, couch co-op games such as Overcooked or Moving Out provide an experience where each player looks at the screen together and are working towards some common goal. You can split up online modes into a couple of categories based on how the computer manages communication between players. The simplest and most common form of online game is a server-client model. There's usually a single server that hosts the game, and all the players connect to it directly. This is common for games like in competitive shooters such as Overwatch or Call of Duty, and is usually required if there needs to be some server authentication. Another model very similar to this is a host model, but it's when one of the clients also acts as a server for the other players. This is very common for games that don't need that kind of dedicated server infrastructure, and many indie games or co-op games that want to have multiplayer, such as Stardew Valley, often use this. The last main type that I'll go over is peer-to-peer networking. This is where every client in the system also acts as a server and responds for shared communication between all clients. Famously, Age of Empires used this peer-to-peer model to manage communication in game state between lots of clients simultaneously, and minimizing the impact of one player with a particularly bad connection. This used to be the common mode for many games, but has fallen out of favor as more streamlined methodologies for server-client and cloud computing have become more popular. Asynchronous gameplay includes games such as Diablo's Marketplace, where players can place items up for sale or purchase items without needing to both be online at the same time. A chess game where players don't need to communicate in real time, as it also follows this asynchronous model. People sometimes play games of diplomacy over email using asynchronous communication, sending an update every week with what all the players decided to do and what happened in the game. Now that we have a basic definition of each of the different kinds of multiplayer, let's look at how they can be implemented on computers. I'm going to let you in on a little secret. Whenever computers talk to each other over the internet, or to a computer right next to them, they use the same protocol to communicate with each other. If you've been playing games for a while, you might be familiar with a LAN party, or a local area network. This is when people would meet up at the same house and connect their computers together in order to play a game online in order to reduce the communication delay that would normally happen if they were playing over the internet. This was very popular when internet speeds weren't as fast as they are now. Although, as I mentioned earlier, the protocols for LAN communication or communication over the internet are the same. The two main protocols that computers use to communicate with each other are called TCP and UDP. These stand for Transmission Communication Protocol and User Datagram Protocol respectively. At a high level, TCP sends data slowly but ensures that it always arrives in the correct order with a bit of overhead. On the other hand, UDP sends data quickly but doesn't have the same guarantees of correctness or order when being received by the other user. Both protocols have their own uses, especially in games. Games sometimes use TCP for establishing connection and communicating user information, while UDP is much more useful for communicating fast updating data such as the state of objects in the game. So for computers to communicate, they need to open a socket using one of these protocols, TCP or UDP. A socket allows for your computer to send data to another computer using an address, protocol, and port. The way that computers can address each other is very similar to how you send mail to other people. You need their address, or in computers' case, Internet Protocol address, IP address. In addition to an IP address, there are also host names which can use the DNS to resolve a host name to an IP address instead of having to use the actual IP data. You can resolve the DNS of any host name by using the ping command on most computers. Host names are often useful for fixed servers as well as authentication. Think of why it's easier to type google.com into your web browser instead of putting that long string of numbers of an IP address into the browser. In addition to an address, the socket also needs a port to open communication. An IP address or host name point to an entire network, while port can only be associated with one computer in that network. Think of it like the IP address is the street address and the port is the apartment number for the address. There can be lots of apartments in the same building, but giving an apartment number helps specify who you're sending the letter to. There can also be lots of computers in the same network, but each port can only be associated with one individual computer. Now, as one last little complexity here, you might wonder, if all computers on the same network have the same IP, how do they send messages to each other? That is a differentiation between a local area network, as mentioned earlier in LAN, and a wide area network, or WAN. Your router does complex work in an algorithm called network address translation, NAT for short, to convert your WAN address to your local address, which is why your computer might have two addresses, a local address for within the network, and an external address for communicating with devices outside the network. This might just sound like a big information dump, but having a basic familiarity of this terminology helps with making network games as well as debugging errors or understanding error codes when you're trying to play a game over the internet. Even though you can make a network game without knowing what an IP address is, understanding what it is and what's happening underneath the hood helps you understand why a buffer might be necessary, or how to properly handle unexpected situations like a player disconnecting and reconnecting. Now that we have a basic introduction to Computer Networking 101, let's move on to the interesting part, game design. The easiest abstraction for thinking about games and synchronization over the internet is to convert your game into a game state. In the context of a game, state is the information associated with the current game to be able to communicate it from one computer to another. For a simple example, let's look at a game of chess. You can serialize the whole game board into a sequence of pieces and what position they are in. Serialization is the process of converting data to a string of bytes or numbers that can be sent from one computer to another, or written to disk. This also extends to more complex data, such as 3D position or velocity data for synchronizing a physics simulation between two computers as part of a game. Although chess is a simple example that only needs to be updated every time a player makes a move or rejoins a game, more complex games with real-time data such as physics objects need a faster update rate and have more parts to consider. The concept of a ticked rate defines how often your game is updated between computers playing a game together. This means that if you want to simulate an object moving across the screen on the server that has a tick rate of 20, then 20 times per second, or every 50 milliseconds, the server will send an update to the clients. Then, whether the client receives an update from the server, they simply need to update the game state accordingly. This kind of synchronization also extends to more complex things such as player input. A player may want to send the sequence of their inputs to the server so that the server can replay those inputs and verify that the player position is accurate and updated. As a simple example, we can look back to the game of chess and say that when a player makes a move, they tell the server what piece they want to move, and from what position and to what position. Then the server simply needs to verify that that move is legal and update the game state accordingly and send the result to both players. Now, while this might work for an asynchronous game model such as chess, this might not extend as cleanly to something like a moving bouncing ball on the screen at a varying tick rate. This is because most of the time we'll be using UDP model for this kind of communication. The reason that UDP model is preferred for real-time communication is because it's much faster than TCP and has much less overhead. However, UDP does not guarantee the order in which packets will arrive. So, given this constraint, if you were to simply update the client state based on every message from the server sent, that object might start suddenly jittering back and forth, as the inputs don't always get received in the same order that they're sent. To get around this problem, a common solution is to use a buffer. This same buffer model is used for streaming videos as well. Whether you're watching a video on YouTube or Netflix, you might see that small buffer space. This space represents the data that has been received but not displayed to the user yet. It's useful to save a buffer so if communication is briefly interrupted, the video doesn't pause or get corrupted. This kind of buffer or delay model is usually accounted for by checking the ping and communication time between the client and the server, and then creating a buffer of that many ticks. So if the ping between the client and server is 100 milliseconds, you might create a buffer of 200 milliseconds, and with a 20 tick rate, this would be about 4 ticks at 50 milliseconds per tick. Then, when the client replays messages, instead of instantly updating the state, we write to the buffer. Then, when we're replaying this buffer, even if the data has been received out of order, we can correct for this by adjusting based on the information in the buffer and that we have for the position of the object. This results in much smoother movement and is usually a standard feature in most multiplayer frameworks. Or if it's not a standard feature, it's fairly straightforward to implement once you know the buffer design for the game. Now that we have our buffer for our object moving across the screen, we still have a problem. We assume that this ball is being controlled by the server using a server authoritative model. The client won't update the ball position and will wait for a message for the server. However, if there is a communication error, we may go a whole second or so without receiving a message from the server, and this ball would suddenly freeze for the client. Since the ball would probably have a predictable motion and path determined by its gravity environment, we can make a good guess at where the ball should be. Since the ball is controlled using a server authoritative model, we don't actually move it at all. Client-side prediction design helps account for this kind of situation. In addition to sending the ball's current position to the client, we can also send the ball's current velocity to the client. This way, if the client misses some data from the server, we can use the previous velocity to guess where the ball would have been. Whenever data is restored from the server, we can overwrite the predicted data with the server's actual data. Client-side prediction is also handy for making even smoother animations. In the perfect scenario where no messages are lost from the server, the ball may move on the server at 60 frames per second, making a smooth image, but on the client, we only get updates for the object at the tick rate, or 20 times per second. Even though our movement is no longer jittery, it's still slower than it is on the server. In the intervening frames, we can apply client-side prediction on the client to animate where the ball would have been in the intervening frames. This may not be necessary for every single object, but especially where the object's motion is predictable, it can lead to a much smoother experience. Additionally, client-side predictions can be extended to more than just physics objects. Earlier we mentioned synchronizing player input between client and server. Most of the time you can assume if a player is walking forward, they'll continue to walk forward. In that situation, if a client misses an update from the server about another player's position, the client can use that player's previous input to move the player how they were moving earlier. This is not a perfect solution and will depend on the game. Also, if we get a prediction wrong, we'll have an unstable condition, and we may see the player move back and forth quickly as that position is synchronizing the server state to the client's predicted state. This is sometimes called rubber banding, as it looks like the object is being snapped forward and backward quickly. Sometimes other states for a game may need to be synchronized but only sent infrequently. An example of this might be a chat log. You don't need to update the chat log at 20 times per second. You only need to update it when a player sends a message. Since we want to make sure that the messages are sent correctly, we can use what's called a remote procedure call, or RPC for short. An RPC allows for a client to invoke a method on the server. Such as adding a message to the chat log or opening a door, the RPC can also be made back to the client, such as sending current state of the data to the game. There's one last concept we need to cover. If we were to only use the server authoritative control and client-side prediction, there would still be one glaring flaw in our game's design. If you want a client to move their own player, they need to wait for their command to be sent to the server, and then sent to the server back for the confirmation. This may be alright for something simple like opening a door, but it would feel horrible trying to move your player. Like, imagine hitting the jump button, then needing to wait for the buffer time of 200 milliseconds to pass before your player actually jumps. To get around this problem, we can change the player object to use a client authoritative model. Under this model, any changes that a player makes to an object that they own happens immediately, and then they send that state to the server. The server simply needs to relay that resulting state to the other clients. This way we have no lag on our player's actions, but can still synchronize the state of other players. This results in each client having a somewhat desynchronized state as I move forward on my screen, but this might take a couple hundred milliseconds or so for your computer to receive that input and move the player on your screen. This leads to each player seeing a slightly different version of all the positions between the clients, and this desynchronization can be resolved with a state buffer and rollback, but that'll be left for a future topic. Overwatch's developers gave a great talk on how to implement this through an entity component system at GDC if you're interested in learning more. For most games, a small desync between clients is no big issue. However, for competitive games, that extra 100 milliseconds of delay could be the difference between who shot first. Sometimes the server will have to decide who wins a fight. Games like Overwatch or Call of Duty use a system called Favor the Shooter, which is, if the player hits you on their screen, the server will usually let that hit go through. Therefore, you may have experienced a frustrating situation where you just ran behind a corner but still got hooked by Roadhog or shot in the back. These concepts of client and server authority, client-side prediction, and RPCs have given you the basic building blocks to make any a multiplayer game. All of these design patterns are implemented by default in most networking frameworks. I'm most familiar with Unity game engine, and there have been quite a few standard network implementations from Unity. The most popular and well-supported of these implementations include Netcode, Photon, Mirror, and Fishnet. Netcode's Unity's official package. Both Netcode and Mirror are open source and free to use. However, depending on the size of your project and resources, paying for a service like Photon, Fishnet, or support for Netcode may be more appropriate for your given project. No matter how you decide to design your multiplayer game, all options have their own advantages and costs. Every game is different, so having a strong foundation of computer networking and multiplayer game design are vital to understanding how to design multiplayer games. As I discussed earlier, my experiences with adding multiplayer to games started back when I was in high school. Gosh, it's been 10 years already since then, but the concepts of computer networking are mostly the same. Send game state between players and manage communication with some servant-client model. I recently converted my OpenKCC package to have a multiplayer scenario, which will be the topic of a more in-depth future video. Multiplayer does make testing more difficult as you'll need to test both the server and client perspective of the project, and there are some drawbacks with multiplayer, like with Unity you cannot host a game with a WebGL build, only a client. Even with these drawbacks, multiplayer has a lot to offer games and allows adding a lot of depth and variety that you couldn't get otherwise. Whenever I make a multiplayer game, I'm always excited to share it with friends, and hopefully you can too next time. Even if you don't intend on making multiplayer games, this knowledge is helpful to understand computers better, including everything from websites to really anything with a computer, which most everything today. Looking at you, Roomba. Hopefully our robot overlords will be benevolent, and they won't remember to switch to IPv6 for their robot armies. Have a great day!